Hello one and all. Today I'm myself Akshar Patel. Today I'm going to discuss about numerical analysis for strength of ships, and I belong to Department of Naval Architecture in Amet. So it's a part of the subjects we call as strength of ships, and there are various things we discuss in the subjects. So today's topic is on what are the numerical approaches available, and we are going to talk about specific topic called finite element analysis. So let's move forward. So in numerical approach we use for various reasons. So as it mentioned here, the disciplines like civil, mechanical, aerospace, and now in the field of naval architecture also we use the numerical approach. Today's talk is on the structural applications, so we'll focus mainly on that. I have mentioned one of the reasons why we do the structural applications. So the main reason is to optimize for the cost, to reduce the weight. So you can see a cantilever beam here. There are different geometries of the same cantilever cut out with small holes, grooves, and the various shapes. Under same loading conditions it has been analyzed. So it is clear that how the stress distribution will be around that. So such analyses are used to reduce the weight of the cantilever beam. That is one of the minor example you can see. Similarly, there can various things one can do. For example, for ship structure analysis, for aerospace and all. Slowly we'll have a look in that. So numerical approach, if we talk specifically finite element analysis, it has evolved somewhere in 1950s. So initially it was developed for structural applications, and with the advancements on the different research and people started working on different topics as well. For example, solving from the simple beam problem to the complex stiffened plate problems, and they come up with the different approaches to do that, and over the time the method has been matured. As of today, there are diverse applications where we can apply FEA so easily and we can get the effective result as well. Some of the methods I have mentioned here, we can see finite difference method, finite volume method, finite element method, boundary element method, and so on. So these are the few methods. They have their own limitations though. Not all the methods one can use for generic applications. For instance, finite element method is highly used for structural applications. It has its limitations when it comes to the fluid mechanics problem. So that is the advantage and disadvantage one of the approximation methods has. So what we are going to understand today is some terminologies. So what are the terminologies are associated with the general numerical approach? It could be finite element method or finite difference method. For instance, there is something called partial differential equation. So when any physical problem you need to represent in terms of mathematical model. Without having a mathematical model, one cannot further simplify it for the analysis. So to represent the actual physical problem into mathematical model, normally almost 90% or more than that, all the physical problems are in form of partial differential equations. So we need to understand those equations. So one terminology which normally talk in numerical approach is PDE. Second one is called numerical techniques. So there are various methods when you can solve the PDEs. When the complexity does increase in the mathematical equations, what happens is it becomes cumbersome task, right? So you do lot of approximations, and those approximations in standard terms we call as numerical techniques. Apart from that, there is something called elements. So you have a mathematical model, you go along with one of the numerical technique. So the first step of any numerical approach would be you discretize the domain, you break the actual problem into small element. So what happens is if it's a beam, I'll take a segments of it, and in finite element analysis each segment is called as element. So a beam can be break down into 10 elements or 1000 elements. It is problem specific. Same goes with any other problems like ship plates or for example bulkheads, side shell, deck plate, and so on. As we know that the problem could be a one dimensional, a two dimensional, three dimensional. In nature all the problems are three dimensions, but under the approximation it can be converted into 1D, 2D or 3D, and based on the problems you need to choose your element type. Normally for 1D problem it is a line element, just a straight line. For 2D there are various geometry for 2D elements. For example, we have rectangle, square, triangle, trapezium, and so on. For 3D, so the 2D elements are called surface element basically, and based on the problem you choose your element type. So again it's the problem specific. About the 3D element, so any 3-dimensional problem is classified, is discretized using the 3D elements. So there are various 3D elements. One you can see it is hexadol, pentatrons, and so 8 node as element, 4 node element, 6 node elements. So again, what is the problem you are solving it, based on that you got to choose the element type. And in the element itself, whether it is a 2 node element or 4 node element or 6 node or 8 node or 12 node. So it all depends on how complex the problem is. So some of the basic terms let's understand further. After element, the next term we understand is called node. So what is node? So as I said, when you break down the problem into small elements, so each element are joined together, and the common point we call as node. So elements are joined together through a node. So the continuity between two elements comes through the node. And the next terminology is called degree of freedom. For instance, if I take a beam, we'll go to types of degree of freedom. Before that, if I take a beam, it's a 1D problem for example, and if you apply the load, under that loading conditions, a beam going to deflect. So it has a deflection. So one of the degree of freedom of the beam is deflection, and there is a slope as well, right? Because it's going to have either quadratic behavior or linear deflection and so on, depending on types of beam and what type of load you are applying. So the degree of freedom here is deflection and the slope. So what is the conclusion here? That you have 2 degree of freedoms. One is translatory, one is rotational. So again, translatory got 3 movements along x, y and z. Rotation got 3, about x, about y, about z. So that called linear displacement, and the other is a rotational displacement. Rotational displacements are normally as slopes. So as you see in this particular slide, any arbitrary shape can be discretized into small blocks, and each blocks can be classified based on the problem. If it is a 1D problem, that block can be called as a beam, bar, column or truss part of the truss. If it is a 2D problem, which normally we face in the ship structures, because most of the elements or the structural components are the 2D, for example deck plate, bulkhead, side shells, bottom plate, inner bottom and so on, and cofferdam. So those things are basically 2D problems. So we have standard 2D problems, for example plates, shells, membranes. So based on their behavior, they are distinct. For example, if I take difference between plate and shell, so plate is a plane geometry, whereas shell is a curved plate. So that's the difference. So degree of freedom for them does vary, and the membranes does not bend, whereas the plate and the shell they have the major problem of bending, whereas the membranes, they are only having axial deformation. So along the axis they deform. So all are the minor characteristics of each of the problems. So here what you say is how the solid can be classified into 1D, 2D. In that 2D it can be plates, shells or membranes. Let's see what are the standard problems available in engineering if one talks about the structural analysis, and I have taken only very few disciplines here. One of the major discipline we call as the naval architecture, where we deal with the ship structures. So you can see a ship drawing here, and under the various loads, for it could be environmental loads like waves, winds, currents. If it is a move to the seabed, then seismic loads, then tsunami effects, so that is part of the wave. And the second category is the aerospace. So a small example which I have taken is the aircraft. So the aircraft wings does act as a 2D problem. It depends on what sort of wing it is. Then it is exposed to the high lift force, the aerodynamic force is coming on that. So that's one of the structural analysis where you analyze the aircraft's wing. Second problem in civil normally we see is the pressure hull. So where the things are stored at the high pressure, at the high altitude at times, or maybe below the sea level. So that becomes your pressure hull problem, where internal pressure and the external pressure under that condition, whether this body is going to withstand that much pressure or not. There was this statistic says that in oceans below 3000 meter, a brick can be ruptured into pieces. So that's the pressure coming on the body if it's something submerged inside the ocean. So that has a different study. And the fourth example is the storage tanks normally. It could be high pressure storage tanks or the low pressure storage tanks. So based on the problem, you got to understand the behavior and then analyze. So these are the standard problems which we face in any structural analysis. It could be naval architecture, aerospace, or civil. This is something interesting. For example, if you have to classify the problem to understand how you are going to solve it, because unless until you have no idea the behavior of the structure, the classifying becomes the tough task to do. So here I have mentioned is 5 classifications. So any structure could be classified the cable or the tension structures. We are always exposed to the tension. In offshore engineering, we have something called teethers. They are the members attached to the offshore platform, mainly TLP, keeps them at the particular station so that they will not move, and they are exposed to the various forces. Second one is called skeletal or the frame structures. So those are the frame structures mainly in the civil discipline, where the various load comes. One of the example you can take is the metal bridge. And the second is surface or the spatial structures. So surface include the shells, membranes, or the plates, where the surface is highly exposed to different type of loading. And the solid structures. So let's take example of automobile. So different machineries we have, IC engines, pumping systems. So there each component could be classified as a solid surface, or they could be whole together, can be called as a solid surface. And the mixed structures. So mixed structures are like in offshore structures we have something called pile and soil interaction, where the pile act as a 2D or 1D problem, where the soil act as a solid mass. So that combination is called a mixed structure, where you have both the discipline coming together, or both the surface and the solid problem coming together. So let's talk about the finite element analysis and understand how it works. So there are 3 blocks. The main block in any analysis we talk about. It could be experimental, analytical, or numerical. So the first block being the physical problem, the actual problem what you have. Again, I'll take an example of cantilever beam, because it's a generic problem for any discipline and one could easily understand. So a cantilever beam could be having a UDL, uniformly distributed load, or the varying load, or it could be a point load, and it is fixed at the one end and the free at the other end, correct? So we understand the physical characteristics of the cantilever beam. So you need to take some assumptions in order to solve this problem, because when the complexity increases, it becomes a tedious task for someone to analyze a particular problem. So there are some assumptions to be made, and then you apply the numerical approach to solve it. So this is the 3 blocks what we normally talk about. So let's talk to what is the first block. So classical problem is nothing but the actual structure being cantilever beam, one example we took, and that actual structure has to be represented in terms of mathematical model. As I said earlier, mathematical models are in the form of partial differential equations. And then the next block is your assumptions. So what are the assumptions normally we take? In any structural analysis, the primary component is the displacement. So you got to have the relations between the various physical properties. So stress and strain, how they are related together, how the displacement is related to the strain, so that once you find the displacement, you find the strain value, and from the strain you get the stress. Once you have the stress value, you can derive the internal forces and moments coming on the structure. So for that we have something called equilibrium conditions, stress and strain laws. So for example, Hooke's law, and once you form those compatibility conditions and the equilibrium conditions, you got to apply those principle of virtual work, those energy methods to further simplify. It is, for instance, suppose there is a cantilever beam whose partial differential equation has the second order of derivative. You apply some of the classical methods or standard methods like virtual work, break down the order of the derivative to the lower order, so that it becomes easier for you to solve and apply the mathematical approach and get the solution, correct? And the next step, the next block, is the finite element analysis, or it could be any other numerical approach depending on finite difference or finite volume. Here we are talking about structural problems. So FA is applied to the structural problems and you get the response. The response could be a displacement, or the deflection in terms of beam, or deformation in terms of plates. If it's a plate bending, it's a deflection again. So what FEA does it? So you have your PDE with you. FEA brings down those partial differential equation to algebraic forms, and then you apply the matrix algebra to solve those algebraic equations and get your answer. So what you see in this particular presentation in this slide is there are three domains where one could study. One is the solid, fluid and the thermal. Since I have been talking about the structural applications, here I am talking about the generic, where the numerical approach can be applied. What are domains? So solid being structural part, where the prime component of your study is how much body is going to displace, correct, under any kind of load. And what are the properties? Your main concern is stiffness, and what is the action here is the load coming on that. The second domain we call as the fluid. In the fluid, what is the main property you have is the viscosity, and what is the action? The body forces. And the response, what you are looking for is the pressure and the velocity, how the pressure distribution will be, how the velocity distribution will be, because once you have that information, you can integrate that and get the answer. And the third one is the thermal. So it's about the conductivity, and my action would be the heat, and the response will be the temperature. So there are different types of loading coming on the structures. So what I have talked till now is we discussed what is numerical approach, the three main blocks of the numerical approach, different terminologies, and followed by the main three domains, the fluid, solid and the thermal. What we are going to talk next is how do you consider loads, different types of load coming on the body. So for example, take a cantilever beam, it is exposed to the point load or the uniformly distributed load, or it could be a different sort of load, correct? So there are four categories normally we talk about. It could be point load, it could be a line load, it could be area load, or it could be volume load. So point load is the specific, it acts at the particular location. Let's take an example. Suppose there is a crane on a deck. So the crane will be, the whole load of the crane will be acting in the particular location, right? So that you could consider as a point load or as a surface load. So what is the surface load? The other term is called area load. It is acting on the specific area. It doesn't cover a particular point. It acts over the area. So it has to be considered accordingly. The other part is called line load. So the best example of the line load would be if you keep something heavy and which doesn't occupy the much breadth, but it occupies the length, correct? So the load acts along the length, and so normally what we do is if it is uniformly distributed along the length, that the particular load is considered as a UDL acting at the particular location. So that is my line load. And the next category comes the volume load. So when all the three dimensions are considered, it is acting on the x direction, it is acting on the y direction, it does act in the z direction as well. So that becomes my volume load. The best example of the volume load would be soil pile interaction case, or the wave interaction with the body, where the wave acts in around the whole area. So that could be the best example for the volume load. Again, it depends on how do you want to approximate your problem, so to make it convenient for yourself. Let's talk about now supports, because we know that no structure exists without any kind of support. If I have to keep something on a table, so without table, if I cannot keep something in air, right, it requires a support. If aircraft has to fly, it has the support coming from the lift developed because of the aerodynamic forces. If ship has to float, there is a buoyancy force which ensures that the ship does float. Similarly, any kind of structure has some sort of supports. Civil structure supported by the ground reactions. Similarly, in ship structures as well, there are various kind of supports we come across. So how to convert that physical supports into the numerical model? So there are different ways of doing it, and the major being, for example, again for making it convenient, cantilever beam. So one end is fixed, other end is free. So it is supported at the one end using the fixed joint. So I'll assume that the one part is fixed, it's not going to move. How am I going to connect that into the numerical approach? So what I'll do is I'll say that okay, I'll take a parameter as that fixed end is not going to deflect. So deflection at the fixed end is 0. Secondly, it is a rigid joint. It doesn't allow you to move, correct? If it either it's welded or fixed inside the wall or any other metal. So what happens is, at that particular point where it is joined, there is no deflection. So I got two conditions there. Condition number 1, there is no deflection. Condition number 2, there is no slope. So similarly, there are various kind of supports. So the first one is the point support, then the line support, area support, and the volume support. So one needs to understand a particular structure in the particular problem, what are different supports we have, because using that idea only you are going to give the inputs to the while doing the analysis. Either it could be a programming or using some commercially available or the open source software. So if it's a line support, you have to give conditions along the line. Suppose the pipe is resting on a seabed, so the pipe is supported along the length. If it's a volume support, so something is put on a ground, say gravity based structures, so they are put on a ground, that could be a volume support or the area support. Or the point support could be a cantilever beam that is supported at the particular location at the point alone, because since it's a 1D problem, it doesn't have other two dimensions, so it normally becomes a point support. Let's further understand what are different types of materials we use, and what are the main parameters on the analysis depends. The number one parameter on which the analysis highly depends on what sort of load you are applying. So if it is a again cantilever beam problem, if it is a point load or the uniformly distributed load or uniformly varying load, because under all the three conditions you are going to have a different response, correct? It's not going to deflect same in all the three conditions, three different response will come. If it is a, and second parameter is the types of structure. So again, is a 1D problem or 2D problem or 3D problem, based on that you will know how the structure is going to behave, correct? So that's very much required to understand the types of structure. And the third category is the response. When you apply the load, body gives the reactions or body responds to it. So what sort of response is going to be, that little bit understanding is important, because without that you might face the issues like how do I manage the conditions, loads, types of support. Say example cantilever beam, when you apply the load, the body is going to deflect. So fixed end is not going to deflect, whereas the free end there will be deflection. The maximum deflection will come at the free ends, and after the results you are going to interpret the results, right? So if you have the understanding about what type of response it's going to give, then it gives a clear idea. As we discussed the different types of response based on the different domains, fluid, solid or the thermal. And material, so there are various type of material. One is called isotropic, orthotropic and general anisotropic. So these are the three categories of materials. There are so many other categories as well. So this gives an understanding for you that what are the material properties going to be constant, or how will you give the inputs of the material property if you know what sort of material is being used for particular structural applications. Let's take about the bulkhead, normally made of the high strength steel. So it falls in the category of isotropic. Nowadays we make structures using composites, right? So composites falls in the form of general anisotropic, because the material property will not be constant at the throughout the body. So the understanding about the what material it is and its property is very important. Apart from understanding the response and the parameters required for the analysis, one should know whether the problem is of what category. In mathematical terms we call as linear, non-linear, static linear, and then again so in static linear, non-linear, again in dynamic linear or non-linear. Because what happens is if the response is non-linear or the problem is non-linear, the complexity will increase. So how will you reduce that complexity under the approximation so that you get the better answer, better in the sense the error will be reduced to a acceptable limit, because when you solve the non-linear problem the time consumption will also increase, correct? So how best to approximate the non-linear problem to the linear problem and understand that's very important. So there are four categories in general which we face: static linear, static non-linear, dynamic linear and dynamic non-linear. So based on that your approach will vary for a particular given problem. So let's move forward and understand what is FEA actually. What we talked till now is we discussed what is numerical approach, the three main blocks, actual problem, how do you represent them as a mathematical model, and then you do the approximation and get the answer. Answer normally we call as a response in structural problems. And we understood different types of load, different types of support, different materials. So this is an introductory lecture. We are not going to talk about how important they are in terms of solving any structural problem using numerical approach, but we just got some idea about it, correct? Let's talk about how FEA works actually. So it all starts about from the idea of you having a discretization of the continuum. What is a continuum? Is any physical problem can be represented in the continuum, and then you break down that continuum into the discrete form. So suppose there is a cantilever beam, you make a thousands or hundreds or tens elements or discretized segments, right? So that's the first step of any numerical approach. In FEA it remains same, and you got to select your shape function. So what is the shape function? So in structural problem, my prime requirement is a displacement. I would like to know, since I have already discretized the domain, how my displacement is going to behave within the element. Is it going to be a linear behavior or is it going to be non-linear behavior? Based on that, I will choose my function which represents my displacement. That function we call as a approximating functions. Later you convert in terms of element, it gives something called shape functions. So it is a whole process. Once you get the shape functions, and you should have before starting the analysis, you should know what is a governing equation, that is a mathematical model. So we use that energy methods and other methods, weighted residual methods, to break down that mathematical model into a matrix equation. So that we call as element equations. So that approximation works there, and we will be having that element equations, and from that element equations we will get something called stiffness matrix. So one must know what is the stiffness matrix for a given problem. If it is a hybrid problem where 1D and 2D problems are mixed together, then the matrix becomes a hybrid. You have to club everything together. And the next is formation of global stiffness matrix. So once you got the stiffness matrix, that is for one element, you got to do it for all the elements, and you got to keep them together, so that when you keep all elements together, it forms a global matrix. So that global matrix is something which we are going to take it forward, correct? That is global stiffness matrix, or you can call a system stiffness matrix also. Then load. So this was about the problem specific. You form your element matrix, you form your stiffness matrix, a global stiffness matrix. Now what kind of load you are going to apply upon that? Is it going to be a point load, surface load, or volume load? That vector you have got to form. So each element will have a load coming on that. So for each element, one load vector will come. Similarly, how you merge stiffness for element to make a global stiffness matrix, same approach to be done for merging all the loads and making a load vector. So once you have your load vector, you got to import your boundary conditions. So boundary conditions, again, it is nothing but what sort of support you are using, at which part particular response is not available, and based on clubbing together you form your boundary conditions. For example, cantilever beam, so one end is fixed, other end is free, so the fixed end will not have any displacement there. Second thing is about solving algebraic equations. So when you discretize or bring down the partial differential equation to small segments, actually FEA gives you algebraic equations. Those equations are put together in the matrix algebra form, and then you solve it. So that's your matrix algebra. And the last part is when you solve those matrix algebraic equations and get your properties, that's the computational properties. So in structural problem, that's the displacement. Once you know the displacement, you can find the other properties as well, like strain, and from the strain you can get the stress, and from the stress you get your internal forces and moment. So that's the flow, the same flow here. Let's summarize quickly. So what we discussed is about the finite element approach, and the main the terms, and what type of load, what type of structure it is, and the process of finite element analysis, right? So discretize the domain, select your shape functions, derive the element equations, merge all element equations and find the global element equations. import the load vector term, what are the loads you're going to consider, and import the boundary conditions, and at the end those algebraic equation you solve it. So this is how it is working. So that's the finite element approach. So what we understood is about the FEA in general, very overview of it. So we touched the surface, we didn't go into detail. So let's see how the further we can discuss about it. Thank you.